Okay, third type of control volume for today is going to be a heat exchanger. Heat exchanger. That's exactly what it's going to be. It is going to exchange heat. Okay, and so there's a lots of different types of heat exchangers that you can see out there. And let's take a look at what a heat exchanger looks like. Okay, so heat exchangers are lots of different types of heat exchangers. Big industrial heat exchangers are going to be shell and tube type heat exchangers. You're going to have big shells where you're going to have a cooling water that's going to flow over a bunch of pipes that have hot water in them. Or you're going to have cold water with hot water going over it. One of the two. You're going to be doing something of that nature. So here's a kind of a flow pattern that you're going to have, the heat exchanger. You're going to have some baffles inside of it that sees how you can change the temperature of one fluid or the other. We're not going to go into the different types of heat exchangers, but you can see that you're going to have those inner tubes, and there's a flow coming over there. So the inner tubes here, and then there's a flow coming over the top of these. Those are going to be industrial size. You'll probably see a heat exchanger that looks a lot like these here. It looks like the radiator in your car, okay, where you're going to have a bunch of tubes and you have a bunch of fins that you're going to have air is going to go over the outside of this and cool off the inner flow that you're going to have going on there. So there's lots of different ways to look at the types of heat exchangers that we might be dealing with in our study, okay. So there are the first type of heat exchanger that we're going to talk about is going to be a direct contact heat exchanger. Okay, I didn't really show you a direct contact heat exchanger. This is your bathtub. Okay, you're in a bathtub like you were assigned to do this weekend, is take a bath. You're sitting in there and your water in your bath becomes very cool and you're thinking, man, I really wish it would warm up a little bit. So what you'll do is you'll put hot water directly in with the cold water and mix it together. And this is a direct contact heat exchanger. How we would draw that, a direct contact heat exchanger, is what we would have is we would have flow 1 coming in and flow 2 coming out, and or maybe it would be say flow 3 coming out, and then you would go in here and have flow 2 coming in here. So this would be T1 or T2 would be greater than T1, and then temperature 3 would be somewhere in between T1 and T2 as it mixes together directly and touches and mixes around. Okay. That's what a direct contact heat exchanger looks like. Sometimes we will call these, in your text, they'll call these an open feed water heater. Okay, an open feed water heater. Okay, in a power plant, the feed water is the water that goes into the boiler. There are times when we need to take away some oxygen, and this is something, again, we don't need to worry about. We need to degas the water. We'll use an open feed water heater. We'll take in the feed water. We'll dump it with some really hot water, and we'll put it into it, mix it up. It'll heat the water up. It'll also do some things while taking out the gases in that water. So notice that will be something that you might see in wording, but I think they'll describe it in your problem statement pretty directly. Okay. The second time we'll have is a concentric tube heat exchanger. Concentric tube heat exchangers look, just like you think. There's going to be two tubes going in here, one going inside the other, and you're going to have two different flows. Maybe you'll have a hot flow go in this direction, and you'll have a cold flow on the outside, and there'll be heat exchange that's going to happen there. Concentric tube. Now, as you see, I drew it in the opposite way. I have hot flow going one direction and cold flow going the other direction. So this can be counterflow is what I have here. Counterflow, they're going in the opposite direction. You could have parallel flow. Where they're going in the same direction. But as you'll find out in heat transfer, it really makes a lot of sense to have them go in the opposite direction. That's going to be the counterflow situation is going to be the most efficient way of going about that. And you also might have, instead of a concentric tube, you might have a cross flow situation. And this is where we're talking about that radiator where you might have a series of tubes where the flow is going in this direction, and then 90 degrees perpendicular to that, you're going to have flow coming through here. So just like in the front of your car, you have your coolant line going through there. You have your, I don't know, your coolant. I used to say coolant, not coolant line. Coolant is going in through there, and you have air that's cooling off your engine, either through that just natural air flowing through. These also can be, you have oil coolers, all sorts of things that can happen where you're using air and that liquid. Notice that this concentric tube heat exchangers usually are two liquids. Cross-flow heat exchangers are usually a liquid and a gas that are working in to help you cool things off. So we can draw these in many different ways. What you're going to see a lot is maybe something called a condenser. A condenser is in a power plant. What's going to happen at the back of a turbine? You're going to have some very high quality steam that's going to come out of the turbine, and you're going to want to take that high quality steam, which means a steam that's in like 95%, and you're going to want to make it all a liquid. And so what we'll do for a condenser is we're going to draw a circle, and we're going to say incoming is there's going to be state 1, which is this is going to be a steam. Maybe our x here is going to be equal to 0.95. And what we're going to have is we're going to have cooling water that is going to be flowing through the condenser. And as that steam goes over the cooling water, it's going to turn into liquid down here and comes out at state 2, where this is going to be saturated liquid. That is one way we are going to draw this. So you're going to see condensers a lot in this class. One of the things we're going to see is how I'm going to draw these as a big box. And this is how I'll draw a counterflow heat exchanger. I'll have this situation, and I'll have this situation. I have maybe here 1 to 2, and then I'll have 3 to 4. So here we have a counterflow heat exchanger. This is the direction we're going. Okay, and we're going to have the heat exchange between these two. Okay, so we'll learn a lot about these in heat transfer, really how we design these. But what we're really worried about here in thermo is how much heat is transferred between those, or the state that's coming out in state 4 or state 2 or whatever. We're going to be looking at it. So when we look at these problems, again, we're going to be looking at our control volume, which means our control volume is largely going to be the heat exchanger enclosure. And we're going to draw it like this. The change in energy of our control volume with respect to time is equal to Q dot minus W dot plus the summation of my mass flow rates N times my enthalpy N plus my kinetic energy N plus my potential energy N, minus the summation of my mass flow rates exiting times my enthalpy exiting, kinetic energy exiting plus my potential energy exiting. Okay, that's what we're looking at. And we're going to go through our typical assumptions here. And we're going to be able to say here our typical assumptions. Well, the first one is going to be what we do for everything. We're going to say steady state. That means that our change in energy with respect to time is going to be equal to 0. So we can take away that assumption. We know here that our W dot is equal to 0. There's not going to be any, you don't have to power a heat exchanger. There's no shaft or electricity that goes into there, so that can go away automatically. Okay. In heat exchangers also, we're going to have the kinetic energy and the potential energy are going to be approximately equal to 0. We're not going to be worried about kinetic or potential energy effects. Okay, kinetic or potential energy effects are not going to go away. But here's the other one that really bothers students when I say heat exchanger typical assumptions. Typical assumption 4 is that Q dot is equal to 0. Okay, now this bothers students a lot. They're saying, what? It's a heat exchanger, Dr. Wanklyn. Why do we have Q dot is equal to 0? Well, it's because we look at our control volume. again, our control volume, we're going to see that there's going to be heat exchanged inside of our control volume. There's going to be heat exchanged inside of our control volume. But we're going to assume that that heat is not going to leak out outside of our control volume. It's not going to have any stray heat transfer. Okay? We're assuming perfect heat exchange. It's going to go from one flow into the other flow and not going to be leaving the enclosure. Now, that's not always the case. In fact, some of your problems will ask for, unless they say solve for Q dot, or say solve for stray heat transfer. Okay, if they ask for the stray heat transfer, they say what heat transfer is straight away and didn't go directly into the other flow. Okay, that's important. So think about this and understand what you're dealing with. Now, if I did want to go up here and I wanted to isolate one of my flows, if I said, okay, now I want to only look at this bottom flow, of course there I'm going to have heat transfer. I'm going to heat transfer that's going to be coming into this flow from the top flow. Okay, that's what's going to happen. But if I look at the whole enclosure, I have to think about what's coming in or what's going out. So think about that with heat exchangers. It's very important. The word you're looking for is there any stray heat transfer? Then you're solving for Q dot. If not, we're going to assume that's equal to 0. So when we get down here, for our equation, we're also going to have 0 is equal to, well, there's going to be two flows coming in, m dot 1, H1, plus m dot 3, H3. And going out, there's going to be two flows. There's going to be minus m dot 2, H2, minus m dot 4, H4. There's two flows coming in and two flows coming out. And we know through mass continuity that m dot 1 is equal to m dot 2, and m dot 3 is equal to m dot 4. So we can draw this as 0 is equal to m dot H1 minus H2. This is m dot, let's say 1, plus m dot 3 times H3 minus H4. So we can do it this way. And now again, because we have their delta H's, we can say if it's a gas, we can say C sub P delta T, or whatever whatever situation we're working with there. We can deal with incompressible substance model and those kind of issues. Okay, but this is going to be a typical way that we are going to look for at a heat exchanger. Okay, so look at that and understand where we're working with that. Okay, that's all we have for heat exchangers.